Okay. All right. So now we are recording this and we are going to look at the test 3. This is a study guide from the previous, from the previous test. So first of all, this is the question that relates to the lab also, and this relates to the, the values for finding the freezing point of a solution. So here is the, let me do it in blue. So here you are given the moles, you are given a formula, you are given the kilograms of water, the freezing point of the solution will be, and you're given the Kf value. So here you are going to use the delta Tf. This is the change in the freezing point. So this is T final and minus T initial. Okay, so there are certain things that you need to know because we're looking at the freezing point. So we are going to have the freezing point of water equal to 0 degrees Celsius. Okay, we need to find this, and then the change is based on the formula. So the change which is based on the formula is Kf is equal to I times Kf times M dash. So for Ne3PO4, so do Na3PO4, Na3PO4. So this is 3 sodium ions, okay, and 1 phosphate ions, minus 3. So total number of, there is 1 phosphate ion. So there are total. So the value of I is equal to 4. Kf is given to you, M dash. Now M dash stands for molality. So molality, M-O-L-A-L-I-T-Y. What is molality? Molality is number of moles of the solute. So moles of the solute over the kilograms of the solvent. Okay. So how will you do this in this case? We are using 0.5. So molality in this case is 0.50 moles of Na3PO4. Divide by, so write this down, Na3PO4. Divide this down by 1 kilogram of, in this case, we are using water. Okay, and this is the molality, M dash. The rest is just fill in the number. So delta delta Tf is equal to, I is, 4 times negative 1.86 degrees Celsius, write down all the units, kilograms per mole, okay, times the 0.50 moles, okay, over 1 kilogram of water. Okay, so here you have, that is delta Tf. So you are going to, in this case, using this formula, you are going to find the value of the change in temperature. Okay, then I'm not going to do all these problems, but I'm just going to walk you through the thought process. So we need to find the freezing point of the solution. That means they're asking you find the T final. What is the final temperature? So the formula would be the rearrangement. T final is equal to T is equal to what was that? So it is T final minus T initial. Yeah. So so this would be T final is equal to, okay. So here is the delta T F minus T initial, and that becomes the T final. So that's the formula you will use to get the next one. Okay. So you will have to do it on your own. I'm just walking you through every problem. Okay. Next, what is the molarity of KCl made by diluting? Now here's a very important thing, diluting. Now they are saying diluting. Diluting means you are going to use the formula M1 V1 is equal to M2 V2. This is the formula for dilution. Okay. What is the molarity of one KCl solution made by diluting 75 milliliters of 0.2 molar solution to the final volume of 100 ml? So that means that M1 is equal to 0.200 M, and M2 we need to find. So what did we do? In the V1, in M1, we took out some, that is 75 milliliters, 75.0 ml. Okay, and then the final volume V2 was 100 ml. Now here's an interesting thing, because generally when it comes to molarity, we change milliliters to liters. But here, since both the units are the same, so you don't need to change. So the rest is just a rearrangement of this formula. So the rearrangement is, we need to find M2. Okay, sorry, M2. And M2 is equal to M1 times V1 over V2. Okay, so just plug in the numbers and you should be okay. So M2 is equal to M1 was 0.200 M multiplied by V1. V1 is 75.0 ml. Divide by the 100.0 ml. So you see the ml and ml cancel out. So that's how you will get the value. Okay. So this is the next one. So you go and practice, do the following, the final calculations. So all the answers are given to you. The answers are given, so you should get the right answer. Okay. What is the molarity of a solution that contains 85 grams of sodium chloride dissolved in 0.50 liters of the solution? Now here, 58.5 grams of sodium chloride. Now this is another way of me checking whether you know the formulas or not. So sodium chloride formula is NaCl. Okay. 58.5 grams. So the formula, always write down the formula. Molarity is equal to moles over moles of the solute over the volume of the solution, volume of the solution in liters. Okay, so now we need to first get the solute, the moles of the solute. So we have 58.5 grams of NaCl. We need to convert that to moles. So to convert grams to moles, what do we need? We need the molar mass of NaCl. Okay, we need that. So what do we do then? So we take Na and Cl. So sodium is 23 grams and chlorine is 35. So the total becomes 58 grams per mole. Okay, 58 grams per mole. So now what do we do? 58 grams per mole, convert that. So 58.5 grams NaCl times 1 mole over 58 grams of NaCl. Okay, so whatever answer you get, that is the moles of NaCl. You're going to put that. Now, the good part is here you are given in liters, so you don't need to change. So this is good enough. Okay, so just put in these moles of NaCl that you find out and divide that by the given volume, which is 0.500 liters. Okay, and that is the molarity. So there is a difference between molality and molarity. Here we looked at molality is kilograms of solvent. Molality is solute over the kilograms of the solvent. But molarity is the volume in liters of the solution. So this is the solution, not the solvent. There's a difference. Okay. All right. So these things. Okay. Next, how many grams of glucose is needed to prepare 400 milliliters of 2% mass by volume solution? Now here is, we are given mass by volume. solution mass by, so we need to find how many grams of glucose needed to prepare. So the concentration is already given, mass by volume percent. And so mass by volume percent, so is equal to 2%. Okay, is equal to, we need to find the mass in grams of the glucose. Okay, glucose, mass of the glucose, and you're going to divide that by the volume in milliliters. And it's okay, in this case, you don't need to change to liters. So this is the 400 milliliters. Okay, so this becomes what? So when you do this, the answer, so this would be 2%. 2% stands for what? 2% means what?
0.02%.
2%.
Or sorry, 0.02.
Yeah, so 2% also means 2 over 100. Okay, so that's easier just to do that. Is equal to m over 400. Okay, so next would be you 2 times. Now I'm not doing the, the mathematical conversions. So zeros cancel out, 2 4s are 8. So this gives you 8 grams of glucose that you need, 8.0 grams of glucose. Okay, so this is the way you will set up the problem. All right. Okay, it looks like we were on track. Okay, calculate the mass by mass percent of the solution made by adding 5 grams of NaCl to 25 grams of water. Now, here's the tricky part. Pay attention to this. This is the solute. This is the water, is the solvent. It's not the solution. The formula is for the solution. So you will have to do the adding. So 2500 grams is the water. Okay, pay attention to that. This is the solvent. And in that, you are going to add 50 grams of NaCl. And NaCl is the solute. Okay, this is the solute. So when you add the two together, so this becomes 2550 grams of solution. And this is the number you will use. So we need to do mass by mass percent. So mass of the solute over the mass of the solution. Okay, times 100%. That's the way to do it. Okay, so 5 grams of NaCl. So this is the way it's going to be. 50 grams of NaCl over 2550 grams of solution. Okay, times 100%. And whatever answer you get, you're going to do it. So just go and practice this on your own also. Okay, rubbing alcohol, volume by volume percent. How many milliliters of alcohol? How many milliliters of isopropyl alcohol is in 475 milliliters container? So container itself means solution. Okay, so it means solution. So understanding this. So we are given 70%. Okay, and that is volume by volume percent is 70%. And how many milliliters of isopropyl alcohol? So we need to find the volume of the alcohol. Okay, and in this case, it is okay to have it in milliliters. Divide that by the 473. Okay, milliliters of solution. Okay, so what will you get in this case? So 70% itself means 70 over 100. Okay, times 473 milliliters of solution. So here's the thing, just so you understand this, 70%, it implies that 70 milliliters of alcohol, or whatever the solute is, alcohol, is present in 100 milliliters of the solution. Okay, so this means 70% implies that. In this case also, what was the thing? This was, you need to find this. In this case, 2%. So this means 2 grams of glucose is present in 100 grams of solution. Okay. Okay, this is what 2% means. Meaning of 2% is that. Okay. All right. Next is, what is the molarity of a solution made by dissolving 5 grams of iron 3 sulfate to enough water to make the final volume of the solution 50 ml. Now, here's the thing. What are we testing here? We are testing whether you can also do the formula or not. So iron 3 sulfate means what? The charge on iron is +3 and sulfate is SO4 -2. And now you do crisscrossing. Okay, crisscross. So this number comes here and this number comes here. So you know the nomenclature naming is continuous throughout. So this is Fe2 brackets SO4 whole thrice. Okay, this is the formula. Now, what is the molarity of the solution made by dissolving 5 grams? So since molarity means moles of the solution over the volume of the, moles of the solute, my mistake. Moles of the solute over the volume of the solution in liters. Okay, in liters. So there are a few things you're going to do here. 50 ml has to be final volume of the solution is given. 50 ml. Convert the 50 ml to liters. So 50 ml times 1 liter over 1000 milliliter. And this becomes 0.050 liters. So this is the volume you will use. Now 5 grams, we need to convert it into the moles. So take the molar mass of iron sulfate. Okay, so here 2 of iron times 56. Okay, and then here 3 of sulfur times sulfur is 32, and oxygen 4 3s are 12. 12 of oxygen times 16. So you add all of this up, and then whatever answer you get, that is the moles of Fe2 SO4 whole thrice. And the next is, what is the molarity? So here molarity is the moles of Fe2 SO4 whole thrice divide by 0.050 liters, and whatever answer you get. Okay, so that's the deal with this. Next is, which of the following compounds? Now these type of questions are all like pretty much theory based questions. So either you get them right or you don't, and you lose points. The good part with the math questions is you can still score partial points. But here you will be, you will be challenged because you either you know it or you don't know it. Okay, so which one of the following compounds will be insoluble in water? Okay, so remember, for these type of insolubility, you have to look at it. If it is the ionic compounds, you're going to look at the table. Ideally, you should remember the solubility rules. But for your class, for your situation, you can just consult the solubility table. Okay, so this is the solubility table. Okay, next is that's one thing. Which of the following compounds will be insoluble in water? Which of the following compounds? Yeah, so that's for the ionic. And then for the covalent, remember ionic ones, always remember, ionic ones will have a metal, always a metal. So you should recognize the metals. And remember, I asked you to memorize the metals, the non-metals, and their charges. So those things. So non-metal, and polyatomic ion. So remember the polyatomic ions. I have given you the handout with all this information. So memorize the polyatomic ions, memorize the non-metals, memorize the metals. Okay, so that's one thing. Next is covalent compounds. Okay, so covalent compounds are those compounds, for the most part, you know, you will be looking at the intermolecular forces for their solubility. So we are looking at the solubility, okay? So for the covalent compounds, the rule is that polar solute dissolves in polar solvent. Non-polar solute is going to dissolve in non-polar solvent. Non-polar solvent. Okay? So that's the thing. So you will have to look at the covalent and the non. So remember, covalent generally contain, let me put it with another pen. So covalents generally like carbon, 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 hydrogen. Okay, number of them. So that makes covalent. So for that, you will have to look the polar and non-polar and go from there. So remember that we talked about polar, if there is an electronegative atom present, unequal distribution, and non-polars are like all carbon, 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 hydrogen bonds, those things. Okay. So which of the following compounds will be insoluble? So in this case, you see, we have, what do we have? Metal, 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 metal. So you are going to consult, if you don't remember, consult the solubility table in the handout. Okay. These ones are polyatomic ion, non-metal, polyatomic ion, polyatomic ion, non-metal. Okay. Now, lithium, group 1A, always soluble in everything. Potassium, group 1A, soluble in everything. Barium, that guy is a troublemaker. Remember Castrobar. Castrobar is calcium, strontium, and barium. So hold on to that one. Sodium nitrate, sodium, group 1A is soluble. Magnesium chloride. Okay, so this one also just consult. So go back and look in the periodic table. No, sorry, in the solubility table and see about the sulfates. So look at the sulfates and look at the chlorides. If you see there is an exception. So in chlorides, there is no exception, right? All chlorides are soluble in water except Castrobar, right? Calcium, strontium, barium, lead, and silver. And sulfates, all sulfates are soluble in water except barium. Barium sulfate is insoluble. So this is the answer. Okay. So this would be as a solid. Rest all of them are equals. Next, which one of the following compound will be insoluble in water? So same story here. Again, we are looking at the non-metals, OH. You know, the what is called the solubility table actually relates to the non-metals or the polyatomic ions more. So hydroxide, all hydroxides are soluble in water except sodium, group 1A. So sodium hydroxide is soluble, but we are still looking at the insoluble. So we need to find which one is insoluble. So here we see that the okay, potassium sulfate, sulfates, nitrates, and chlorides. Okay, so here once again, sodium is group 1A, will be soluble. Potassium group 1A is soluble. Lithium group 1A is soluble. So now we are comparing the lead, and we are comparing the lead sulfide, and we are comparing magnesium. So once again, magnesium, all chlorides are soluble except calcium, strontium, barium, and so lead. So this magnesium chloride will be soluble. Now look at this solubility table. Look at the sulfides. So look at the sulfides, and you will see that all sulfides are insoluble except group 1A and ammonium. So this is going to be the one that is solid. Okay. So this is the way, you will have to use some elimination in case you're stuck on the test. Okay, which of the following compounds will be soluble in water? So you see so many questions on solubility are coming because you've done the labs on these, so you kind of have an idea. Okay, so here we have the soluble. So now we are going to look at whether they're soluble in one or not. So once again, look in the look in the solubility table. Look at for the chlorides, hydroxides, chloride again, sulfate again, and carbonate. Okay, so all chlorides are soluble in water except All chlorides are soluble in water except castrobar and mol. In other words, calcium, strontium, barium, mercury, aluminum, mercury, silver, and lead. So this is going to be solid. Copper hydroxide. All hydroxides are insoluble in water except group 1A and ammonia. That's what the table reads. So this is going to be solid. Lithium chloride, because it's a group 1A. So this is going to be soluble. So AQ. Okay. Calcium sulfate. All sulfates are soluble in water except barium, strontium, calcium. So this guy is solid. Next is lead carbonate. All carbonates are insoluble in water, right? Except group 1A and ammonium. So this will be solid. So the question here was asking about what is soluble. So you get it now. Okay. Next is the process. This is a term, a definition. The process by which the semi-permeable membrane, so that it relates to osmosis or osmotic pressure. The process by which semi-permeable membrane allows water molecules, small molecules and ions to pass through while retaining large particles is called, actually, in this case, it is dialysis, because semi-permeable membrane only, so osmosis only allows the, so for, if it is just the osmosis only allows the filtration of water through the semi-permeable membrane. But when we talk of dialysis, then it's not only allowing water molecules, it's also allowing small molecules and ions to pass through. So think about, like, more is being passed, and these are artificially manufactured, membranes, not naturally occurring. Okay. All right. Next, now comes these type of questions. Again, theory-based questions can be difficult if you do not understand or if you don't read. So you have to read also. Okay, methanol. Methanol is the CH3OH, can be classified as a gas, a solid, a weak electrolyte, strong electrolyte, non-electrolyte. Okay, now, first of all, it's a big molecule, CH3, and then it has got OH. So how would you know whether it's a gas or not? So here's the thing, CH3 is this, and it's methanol. Methanol by default is like alcohol. Okay, and here oxygen. So there is going to be, in this case, it will be like water. Okay, so it is not going to exist as a gas. If you freeze it, yeah, it will exist as a solid, but at room temperature it exists as a liquid. So that's one thing. So these first two are eliminated. Next is weak, strong, and non-electrolyte. So this is the formula. We show this formula in the class, we cover it. So here's the formula. So there is going to be hydrogen bonding here, right? Because of the OH. And there is dipole here, dipole, right? And it has London dispersion. So all these forces are present here. So that's one thing. That's why it is going to exist as a liquid. But it is a non-electrolyte. Partly, remember, I told you for the non-electrolytes, there has to be carbon-carbon bonds, the whole bunch of carbon-carbon bonds, and carbon and hydrogen bonds. Okay, carbon-carbon and carbon and hydrogen bonds. So that is non-electrolyte. So that's not going to ionize. So this is will not ionize. Therefore, even though it has all these, strong intermolecular forces, it will not ionize. Therefore, it is a non-electrolyte. Okay, it will not. Electrolyte is only when they ionize. Strong electrolytes, 100% ionization. Weak electrolytes, just keep this in mind. Weak electrolytes are the ones, again, that contains lots of carbon, 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 hydrogen bonds. Okay, they will form weak electrolytes. But if this one will not. So this is something, you should just know. Just know this. Okay, because you're not there yet for the organic chemistry, but for the knowledge, this is important. Okay, how's Henry's law? Henry's law relates the relationship of pressure and solubility. Okay, so when the pressure goes up, solubility of the gas goes up. When the pressure goes down, solubility of the gas goes down. Okay, so here, as the pressure increases above the liquid, so according to the solubility of the gas increases as the gas pressure above the liquid increases. This is the answer. Okay, next is an increase in the temperature of a solution usually now increases the boiling point. Increase in the temperature. So that, I mean, some of them are just doesn't mean. An increase in the temperature increases the boiling point. Increase in the solubility of the solution. So for increase in the temperature of a solution usually increases the solubility of the gas. No, this is wrong. When the temperature increases for the gases, the solubility goes down. So this is not the right answer. Okay, increase in the solubility of the solid solute. That is right. For the gas, for the solids, it's opposite. Increase in the temperature, the solubility increases. So this is the for the solids. So this is very clear difference. Decrease in the solubility, no. Decrease in the solubility. So this is the like this is the like the relationship that you need to know. So this is the answer. Okay. Now, next is the in water a substance that dissociates completely in a solution is called dissociates completely is obviously going to be a strong electrolyte. 100% dissociation in water, 100% ionization. So strong electrolyte. Next, oil does not dissolve in water. Now, oil contains lots of carbon-carbon and lots of carbon-hydrogen bonds. So it's a lot, okay? So that makes it, oil makes non-polar. And so the rule is like dissolves like. Water is all the time polar. Water is polar, always. So polar and non-polar will not mix. So the answer is, it will not dissolve because oil is non-polar. So the rule is like, we are testing whether you know, like dissolves like. So polar and non-polar. Okay. Next is the boiling point, water at sea level. At higher altitudes, the boiling point. So remember, when so the pressure at sea level is like about 760, sorry, or just put it here, 1 atm. 1 atm. Actually, it's not even at the sea level. We call it sea level, but it's actually on the plains. Okay. So the boiling point of water at sea level is 100. So that's the standard at standard temperature pressure rather. So at 1 atm pressure, when the pressure is 1 atm, the boiling point is 100 degrees Celsius. Now, when you go on the hills, the hills pressure is less than 1 atm. Okay, the boiling point of water at sea level is 100. At higher altitude, that means hills, the boiling point of water will be, so when the pressure is low, the substances are going to boil at like less than 100. So boiling point will be lower than 100 degree Celsius. So things will boil faster. Okay, so lower because atmospheric pressure is low. Next is water is a polar solvent and hexane is non-polar. So again, water is a polar solvent and hexane. So again, carbon-carbon. So C6H14, non-polar. And water is polar. So they don't mix. Okay, they do not mix. No mixing. Okay, so which of the following correctly describes the solubility? So remember, it's the like dissolve, right? So oil, so again, oil and water will not mix. Calcium chloride, soluble in hexane. Hexane is non-polar and calcium chloride is like a solid. So this is also not going to dissolve. This one won't not dissolve because remember, all chlorides are soluble in water except barium, strontium, calcium chloride. So next is sodium bicarbonate, soluble in water. Sodium bicarbonate, and sodium bicarbonate is sodium group 1A. Sodium group 1A, always soluble in water. Anything it attaches to, always soluble in water. So soluble in water due to the solvation of ions. Okay, so in this case, this is the right answer, because water is polar and this is soluble always in water, so polar mix. Carbon tetrachloride soluble in water. Carbon tetrachloride is this. Remember, you have to do the low structures like that. Okay, so what happens here? This becomes non-polar. Although each single bond is polar, but carbon tetrachloride is non-polar. So this will not mix in water. Okay, octane. So okay, you guys don't know octane. Octane is C8 and H 17, 16, 17, 18. So this is again carbon. So all these weird names, octane, butane, propane, hexane, heptane, all these are like carbon containing compounds, carbon and hydrogen. So that's why the answer is that. Okay. Next is vapor pressure can be described as vapor pressure. This is the pressure that is over the liquid of, so pressure exerted by the liquid vapors. So the temperature at which the bubbles of the vapor appear. No, vapor pressure is the pressure exerted. So it's obviously not the temperature. So these are, it's not a vapor pressure, is not a temperature. So let's look at this. So eliminate these. The next is the pressure exerted on the earth by the particles. No, vapor pressure deals with the vapor, like the water vapor. So it generally deals with the liquid. Okay, so it has nothing to do with the earth's pressure. The pressure exerted by the gas above the surface of the liquid. This is the right. Next is pressure within the lungs during, so that is again not, so it's the answer is D. So this is like, the terms, definitions. So if you are writing the term paper, then you're okay. Okay. If you're writing the definitions, then you're okay. All right, now let's see how many more are left. Okay, let's go ahead and finish this. Okay, so next is 20 degrees so here, okay, you are given 570 millimeters of mercury, 25 degrees Celsius. A gas sample has a volume of milliliters. What is the final pressure in millimeters of mercury in a volume of 2560 milliliter, and the temperature is this, if the moles are constant? So let's write this down. Everything that is given to us, we are given final pressure. So we need to find the final pressure. And so we are given P1, V1, T1, and P2, V2, and T2. P1 is 570 millimeters of mercury. So write down the units, write down the numbers, okay? And next is, we are looking at the temperature, okay? Next is the V1, V1 is 2270, 2270 milliliters, okay? Temperature is 25 degree Celsius, okay? What is the final pressure? P2 we need to find, V2. V2 is, what is the final pressure at a volume of, V2 is 1250 milliliters, 1250 milliliters, and the temperature is equal to 175 degree Celsius. Okay, now few things here. Always convert this to, so do this, 273. Okay, now here this is milliliters, so leave it as it is. This is in milliliters. If there was a change, then you needed to change it. Now, what is the final pressure in millimeters of mercury? So they want it in millimeters of mercury, so we don't need to change it. So we will keep this here as it is, and we will have the final pressure in millimeters of mercury. So this is based on the formula P1 V1 over T1 is equal to P2 V2 over T2. And remember all the rearrangements we did. So the formula you're going to now use is P2 is equal to P1 V1 over T1 times T2 over V2. Now this is all, see guys, this is the algebraic conversions, okay? Algebraic conversions, and that is, you should know how to do this because the prerequisite for this class is algebra 1. Algebra 1 is the prereq. So I have given sufficient, worksheets, but sometimes they're not enough because those are just going to give you the little bit of the review. So the main thing was, it was important, as was told on the very first day of the first few weeks of the class, that this class needs a prerequisite, okay? Algebra 1, sorry, but I'm written here. Algebra 1 prerequisite. But if you have not done that, then you will have to just sit with the tutors and do it. Algebra 1, okay? Sit with the tutor and figure out, and the rest is just punch in the numbers. You should get, this is what I'm giving you, I'm helping you with these. At least you should be able to plug in and do the math, okay? Otherwise, we expect that you should be able to do the conversions yourself. Anyways, let's look at it here. A tank contains helium
I have
gas.
a question.
Yeah, go ahead.
Do we have to know the formulas of the organic chemistry compounds like methane and octane?
No, you
Because
don't.
it was in some of the questions.
Yeah, but right now I'm telling you, okay, you don't need to know, like, okay, you don't need to know, but okay, you guys did the nomenclature for the non-metals.
Yeah, you told us to skip the organic chemistry parts.
Yeah, I asked to skip the organic, but I'm just trying to tell you that the naming, okay? So mono will be 1. So that same terminology applies here also. Di is 2, tri is 3, and what's the other one? Tetra. Oh, actually, no, not really. Tetra is 4. I mean, some of it. Like penta is 5. So that pentane. Hexa is 6. Hexane. And then hepta is 7.
I guess I just wonder if we need to know the structures for some of these questions.
No. So just try to just understand, if you see something like this weird octane, or which was the other one? There was a few, heptane or pentane, like that. They are organic compounds. So just assume that, just keep this in mind, that they're going to be carbon and carbon, or carbon and hydrogen bonds. That's it. Okay. Got it? Like this one, hexane.
Carbon and carbon or carbon. Okay.
Yeah. So just keep that. You don't need to know these guys, all organic compounds have carbon, carbon, and lots of carbon, carbon, and carbon and hydrogen bonds. And then they can have more also, but that's the main cage, the main, the main, what do you call, the main structure of the molecule. And then there can be more, oxygen or nitrogen or chlorine. That's not okay. So but like I said, heptane is 7 carbons, octane is 8 carbon, hexane is 6 carbons, pentane is 5 carbons, butane is 4 carbons, propane is 3 carbons, like that. So, but you don't need to know the formulas. Don't worry about that. All right. Now let's look at the next one here. A tank contains helium gas at 470 millimeters of mercury. So 470 millimeters of mercury relates to pressure. Nitrogen is the gas, so nitrogen N2. Okay, at atmosphere at 0.75 at ATM. So 0.75 atmospheric pressure is helium gas. Oh, sorry, helium gas is, 1 second. Helium gas is at 490 millimeters of mercury. Nitrogen gas is at 0.75 atm, and neon is at torr. So now, interestingly, so this is for this one. So call it helium, pressure of nitrogen, and pressure of neon. Okay, what is the total pressure? Now here we are testing your formula, and we are also testing your conversions, whether you know how to convert them. So here, pressure of helium plus pressure of nitrogen, partial pressure, plus pressure of neon. But none of them have the same units. You see that? This unit, millimeters of mercury, this unit, ATM, this unit, torr. Okay, so we have to equalize them, make them all one. So we know certain things. We know that 1 ATM is equal to 760 millimeters of mercury. Okay, and 1 ATM is equal to, it's easy to do with ATM, less numbers, right? So is also 760 torr. So in this case, we want to make sure that you understand nitrogen, no need to convert, but you're going to take for the partial pressure of helium, and that is 490 millimeters of mercury, okay, times 1 ATM over 760 millimeters of mercury. Let me move this here, all of it. 1 second. Okay, so partial pressure of helium is equal to 490 millimeters of mercury. So show all this conversions times 1 ATM over 760 millimeters of mercury. Okay. Next is neon. 520 partial pressure of neon is 520 torr times 1 ATM over 520 torr. Okay, so here millimeters of mercury cancel out, torr cancel out. So whatever answer you get here, you're going to then put those numbers in the main formula. So they want you to find the total pressure, but we want to see that you use the converted values. Okay, so this gives you the pressure of helium in ATM, and this gives you the pressure of neon in ATM. Okay, so these values, got it? All right, now you are given the moles of hydrogen gas, which has a pressure is given and a temperature is given. So write this down here. So moles of hydrogen gas is equal to 0.250 moles. Okay. Then the value of the pressure is 1.70 atm. Okay, and the temperature is 35 degrees Celsius. Okay, so you add 273 to it. Just do it by practice, and that will give you the value of temperature in Kelvin. So this is important. Now, something that is not given here. So what volume? So we need to find the volume. Volume we need to find. Okay, so this is based on the formula PV is equal to N R T. Okay, volume is equal to N R T over P. Okay. Okay. Now, something that is, remember, when pressure is in ATM, the value of R, this is something you should know, or you should write this down. And also this information is in the handout also. Okay, so just see where it is in the handout. So R is 0.08206 liter atmosphere per mole K. Per mole K. Okay, but pressure in millimeters of mercury, the value of R is, I believe, 62.4 millimeters of mercury liters per mole K. So there is a difference between the two. So just make sure that you are using the right value of R. Okay, so this is the R value you are going to plug in. Okay, so you have the moles, you have the temperature, you got the Kelvin, you got the value of R, just plug in and you will get the volume in liters. Okay, so here I think I forgot, yeah, this one, yeah, make sure always convert the temperature into Kelvin. Okay, next is a sample of argon gas at 300 degrees Celsius. So that's the temperature at 50 atm. so that's the pressure, is cooled in the same container to a temperature of 0 degrees Celsius. So this one was T1, this was P1, this is T2. What is the new pressure? So we need to find P2. So here, this is based on the Gay-Lussac law. So P1 over T1 is equal to P2 over T2. Now here, you understand this, we are given this is in 0. That is why the whole thing is going to become 0. This is the reason why you need to convert the temperature into Kelvin. So pressure, okay, so the pressure is fine. Pressure we don't need to change. Temperature we need to change. So this one plus 273 and this one plus 273. Okay, 273. Okay, so now we will see, we need to find the what is the new pressure? P2. P2 is equal to P1 over T1 times T2. P2. Okay, so here you will just put in the plug in the numbers. P1 is given 50.0 atm over T1 is 300 plus 273, and then T2 is 273 plus 0. Okay, so that thing. Next is the theory again. An autoclave is used to sterilize surgical equipment because now autoclaves are where you put the syringes, right? Or any surgical equipment, and very high pressure. Autoclaves have pressure is very high. And the reason why they want to put the pressure high, so that the boiling point of water increases. So the water should boil above 100 degrees centigrade. So the syringes can stay, in extremely hot water with temperature above 100 degrees Celsius. So, and the water will not boil, right? So this remain in the hot water. We want to kill the bacteria, okay? That is, sterilizing means killing bacteria or viruses, all those things, okay? So autoclaves, just remember, in autoclaves, the pressure is very high. So the boiling point increases. The water will now boil at a high degree. So it allows water to boil at a temperature above 100 degrees Celsius. That is the only reason. The rest is all nothing. Next is, okay, this one we have not covered in the class yet, in the lecture, but I'm still going to do it here. The force of collision of gas particle against the wall of the container is called pressure. That is, we discussed this. This is the pressure. No, I think this is all okay. The other one, the other pizza. Okay, so here, this is the gas particles inside the balloon. So they are colliding, and their collisions are elastic collisions. Okay, and so what are these elastic collisions? They are bouncing off of each other. They are bouncing off the walls. Okay, bouncing off the walls of in this. So they are just tick like they bounce off. So the force with which they strike the walls, because remember, gases want to escape. So they are looking at the escape route. So they hit the walls of this container so that they can, leave, but they cannot find it. So that's why they keep bouncing off of each other. So, but that thing is called pressure. Pressure is the force with which they exert, the force they exert on per unit area. That is the pressure. Okay. Now, this is the one I was talking about, the chapter 20, this one. The next chapter is on the rates of reaction and equilibrium, which will be covered in class, but we are going to, I'll still do this for the review. So catalyst is something. So again, this is a definition. Do you know the definition of catalyst? Do you understand how it works? And, so catalyst is a substance that speeds up a reaction, that increases the speed of a reaction. without being consumed in the reaction. So in other words, it is not a part of the final product. It's not getting consumed, but it does do certain things, like it provides surface area, so reactants can rest on it. Okay, it provides the surface area, it provides the surface area, and then it provides the alternate pathway. It shows the reaction, shortens the pathway. It provides transportation, right? It acts as a transportation. So the substances, they can load on that path, that enzyme, like, or the catalyst, and then they can go from one place to another. Okay, and then it offloads. So it's like that. So it is not a part of the final product. It may take part in the reaction mechanism, but not a part of final product. So it is not a part of the final product. It just take part a reaction in the middle little bit, and then it just detaches itself. Next is the activation energy. This is the energy that is needed to start the reaction, initiate the reaction. Okay, there's always that. So activation energy is it brings the temperature down that is needed to break the bonds. So initiate the reaction means breaking bonds, the energy that is needed to break the bonds. Okay, so that energy, it's less energy, the bonds can be broken. Next is in the following gas phase, what is the effect? So this is the Le Chatelier's principle. So this relates to disrupting the equilibrium. Okay, so here you are given 6, 2. Okay, so there are 3 moles here, and there is 2 moles here. Okay, let's see. In the following gas phase, what is the effect in the direction if more SO3 is added to the mixture? So more SO3 is added. So more SO3 added. So the reaction is going to move backward. Okay. So the equilibrium shifts to produce more reactant. So moves backward. So the concentration of the reactants is more than the concentration of the products. Okay, next, if the volume of the container is increased, the amount of PCl5 in this reaction. So if the volume, so here, this is 1 mole total. This is 2 moles total. Okay, so total moles. Total on each side. Okay, so here we have 1 mole and 2 moles. If the volume of the container is increased, so it's always the reaction moves in the direction where there is more moles. So if the volume increases, the reaction is going to move in the direction where there are more moles. If the volume decreases, the reaction is going to move in the direction where there are less moles. So if the volume of the container is increased, the amount of PCl5, now PCl5 is less. So in other words, so the reaction is going to move. So volume of the container increased, so the reaction moves in the direction where there are more moles. Moles are more, okay? Then that means that it's going to move. So in this case, it is going to move forward. And when it moves forward, that means there are more products than the reactants. So it will, so that means the PCl5 will decrease. PCl5. So we will discuss this in the class. The equilibrium concentration of NO2. So now this relates to the KEQ is equal to the products, concentration of the products raised to the power moles over the concentration of the reactants raised to the power moles. So here we have this reaction. So concentration of N2O4 over the concentration of NO2 raised to the power 2 is equal to KEQ. So here, the equilibrium concentration of NO2 is N2O4 is 1.0 and NO2 is 0.38 raised to the power 2, and this is going to give you the value of KQ. So always remember that. So this would be 1.0 over 0.38 times 0.38. Square means that. So that is going to give you the value of whatever, you will get. So that is going to be equal. So KEQ, that's the no units. Okay. All right. So that finishes this chapter. So these type of questions will be on the test. Just study them, theory, right? And I'm going to just now stop sharing and
Thank you so much, Professor.
recording 1 second. So it stopped recording, right?
Yes.
Okay. Oh, it's still recording now, actually. Why is it saying? Okay. Stop.